Hi, today's lesson is about probabilities from tree diagrams. So we've looked at Venn diagrams and tables already. Tree diagrams are another way to present data so that we can work out probabilities from them. Now, you've done a lot of work on tree diagrams in the past, and so a lot of this lesson is about trying to extend your knowledge. Okay, we use the word event in statistics to refer to a possible result from a trial or an experiment. So an example would be a seed growing into a red flower, a 6 being shown when we roll the dice. They are all events. A tree diagram is about trying to find the probability of 2 or more events. So here's our example. There are 5 chocolates left in a box, all looking the same. 3 raspberry creams and 2 nougat, nougat chocolates. So nougat, I believe, if you ever had a Mars bar or a Moro bar, it's sort of that light brown part underneath the caramel underneath. I think that's nougat. So what we've been asked to do is to draw a tree diagram to show the probabilities if 2 chocolates are taken at random. Second of all, find the probabilities if you choose those 2 chocolates that they're both being nougat. The second situation is the first being raspberry cream and the second being nougat. Third one being that you get one of each type. So, usually with a tree diagram, you start with a blank canvas, and what we have to do is think of the situation. So we've got 5 chocolates, 3 raspberries, 2 nougats, and we've got 2 events. So event 1 is choosing one of the chocolates. Event 2 is choosing 2 of the chocolates. So if we think about the first event, 1 chocolate, how many outcomes are there? Well, there's 2. You either choose a raspberry, or a nougat. So you need 2 branches. Now, when we think about our second chocolate, and sorry, we labeled them R and N. Another way of doing it, you could replace, if you wanted to, N with the complement of R, meaning not raspberry. But in this case, it's relatively easy to do. 3 of the 5 chocolates are raspberry. So if we think about the probability, that means the probability of going down this branch or choosing a raspberry is 3 out of 5. Now, thinking about the nougats, it must be the 2 that are left over, so it's 2 out of 5. The key thing that we must realise is that that these add up to 1. So now that's the first event sorted. We now think about the second event. Second event, what if I chose a raspberry first? What are the options? So for the second chocolate, I could choose a raspberry. Okay. Now to get the probability, what we have to think about is that we're already chosen one of the one raspberry already. So there's 1 less in our bag, and also there is 1 less raspberry. So that's why we end up with 2 over 4. Okay, so you can see that 3's reduced by 1 and 5's been reduced by 1. Now what that means for our nougat is that we still have 2, but rather than it being out of 5, we've now got 2 left. Now, looking down the nougat branch, because I chose a nougat first, it means that there are still 3 raspberries left. So that's going to be 3 out of 4. And if I look at this branch, you can see that there's 5. So with the nougat choice, because I chose a nougat already, means that we now only have 1 left. So it's 1 out of 4 there. So you'll notice that the total of each of these little branches add up to 1 as well. Now, if I want to work out the probability of each individual branch, for instance, if I wanted to work out the probability that we get a raspberry and a raspberry, I multiply along the branches. Okay, so to do that, what we end up is 3/5 times 2 quarters, which gives us 6 out of 20. Now, if I want to work out the probability of getting a raspberry and a nougat, then I have to multiply those fractions together, which is 3/5 times 2/4, which is 6 over 20 as well. Working along the nougat raspberry branch, what we end up with is 2/5 times 3/4, which is 6/20. And the last one, we've got 2/5 times a quarter for 2 nougats, which gives us 2/20. 2 out of 20. Now, the big thing that we should notice is that all 4 probabilities add up to 1. And that makes sense because we know if the probabilities equal 1, that's all the possibilities. There's no other possibilities for choosing in this scenario and getting a different result. You either get a raspberry and a raspberry and nougat, nougat raspberry, or a nougat and nougat. And now we have their individual probabilities. So now that you've done your probability tree, you can start to look at the questions. So the first part is looking at what is the probability that we get both get nougats. So first of all, identify the branch, which is along the bottom there, and that you can see equals 2 out of 20. So there's our answer, which we can simplify to 1 out of 10. Notice we didn't simplify these things earlier because of the next stage, which is looking at the probability of getting a raspberry and then a nougat. So that's looking at that branch. You can see that's 6 out of 20, which simplifies to 3 over 10. Now, the probability of getting one of each type. Now, looking at our probability tree, there are 2 ways that you can get one of each type. You either get a raspberry and a nougat, or you get a nougat and a raspberry. Now, this is part of the reason why we didn't simplify the fractions earlier, is that if we need to look at the total probability there, we have to add them together. And adding makes it a lot easier when the denominators are the same. So add them together. So that's the equivalent of getting a probability of getting a raspberry, then a nougat, or a nougat, then a raspberry. Which we add that together gets 12 out of 20, which simplifies to 3/5. So to summarize what we covered just there, a tree diagram shows the probabilities of more than one event. So you can do 3, 4, 5 if you need to. Once you get up to 5, though, it starts to get a little bit messy trying to cover everything, but it certainly would be possible. To find the probabilities for each branch, always assume the event on the branch leading to it has occurred. So in other words, the first event happens before the second event. So the other thing that we've got here is that the first event assumes the second one has occurred. If you are given a word like replacement, like for instance, if the chocolates were replaced back into the scenario, the probabilities wouldn't change. We call this independence. So if you're also told that they're independent, and the probabilities don't change from event to event. However, if they are dependent, then we say that the probabilities do change. To find the probabilities of two events, you multiply them together. So the probability of getting A then B, or A and B, you multiply them together to get 5/8. And the to find the probability of one or another event happening, add the individual probabilities. So for instance, if we want to know whether we're going to get A and C or B and D, we have to add those together. Here are a couple of questions to have a go at. So the first one looks at, there are 4 red and 6 blue biros in a drawer, so pens. 2 are taken out at random. Draw a tree showing the probability of each event. A is the first. The first is replaced before the second is taken. In this first one, in B, the first is not replaced before the second is taken. So that's what I was talking about before. This is an example of an independent and therefore the probability from the first one won't change to the second one. And this one is an example of a dependent probability, because depending on what you choose from the first one will change what happens and what the probabilities are in the second one. The second question is looking at the components for a machine are supplied by 3 factories, A, B, and C. 45 come from A, 25 come from B, and the rest come from C. Data shows that 4% of those from A and 5% of those from B and 2% of those from C are faulty. Draw a tree diagram showing all the probabilities. Use it to find the probability that a randomly selected component is faulty. So have a go at this. Grab a piece of paper. Think about what are the 2 events in each one. Draw out how many outcomes are there for each one. Put the probabilities in and try and find the answers to the questions. So pause the video now. Okay, hopefully you gave that a go, and let's see how you get on. So question 1 looks like this. There are 4 red and 6 blue, so 4 red, 6 blue. So we should end up with that. And because we're using replacement, it stays the same for the second event. So the probability of getting 1 red, 1 blue is going to be 1 red, 1 blue is going to be 24, 1 blue and 1 red, 24 out of 100. Add together gives you 48 out of 100, which simplifies to 12 over 25. So if we look at B, where things are not replaced, it's the same tree diagram, but you can see here that rather than it being 4 here, it's now 3 in the second one. Because you've chosen a red first, it reduces down. Likewise, there are 10 pens in total the first time. Because it doesn't get replaced when you choose it the second time, it reduces to 9. So it makes a big difference looking at that not replacement thing. Again, make sure the probabilities add up to 1 and all that sort of stuff. What we end up with is 48 out of 90. Sorry, 24 and 24 out of 90, which gives us 48 over 90, which we simplify down is 8 over 15. So you can see that it's actually, it's slightly more likely to get one of each where it's dependent. So if we take a look at question 2, okay, the components for a machine are supplied by 3 factories, A, B, and C. 45% comes from factory A, 25 from B, and the rest comes from C. And then we look at how faulty those components are. So the key thing is setting up your diagram. So first of all, it's the factories. Then second of all is whether it's faulty or not. Another option, rather than using N here for faulty and not faulty, is that you could say faulty and the complement of faulty, which is not faulty. It just makes it easier sometimes with the notation and not getting confused with different outcomes. So now that I know that, then what we can do is start putting in the probabilities. So A we know is 45%, B is 25%, C is the rest. So if we add those together, we get 0.7. So it must be that it's 0.3 for factory C. Now, second of all, we know that 4% of the faulty components come from factory A, meaning that there's 96% that are not faulty. For B, we know 5%, so slightly more, and that means 95 are not faulty. And lastly, 2% are faulty with C, 98 are not faulty. So if I want to work out the probability that any component I choose, whether it comes from A, B, or C, that I randomly select one, what is the probability it's going to be faulty and it's come from A? Sorry, first of all, it's come from A and it's faulty, is I multiply across those lines. So 0.45 times 0.04. And if it's not faulty, we get 43% by multiplying the numbers. Therefore, I can go over and calculate all the values. So multiplying along the branches. So once you've got your tree diagram, answer the question. So what's the probability you get a faulty component? Well, then it's the probability that you get a faulty A, a faulty B, and a faulty C, which is 0.6, 0.0125, and 0.018, which gives us our final answer, which is 3.65%. All right, that's the end there. Go to your workbook or the PDF off the lesson page and have a go at some probability trees.